Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on August 27, 2025, just yesterday. The standout result is a trainable planner and executor agent that breaks the usual trade-off, delivering robust execution and strong cross-domain planning. And it sets a new open-source state-of-the-art on the Science Board benchmark. The paper is titled CODA, Coordinating the Cerebrum and Cerebellum for a Dual-Brain Computer Use Agent with Decoupled Reinforcement Learning. And as we'll see later, the results are really impressive. In short, the method couples a generalist planner with a precise executor using decoupled reinforcement learning and a two-stage training pipeline. Also, the authors shared an official implementation on GitHub. You will find a README with setup steps, CODA and VLLM requirements, Science Board integration, and inference instructions. There are scripts to deploy the planner in executor models, run evaluations across VMs, and notes on planned training code and a judge model release. On Hugging Face, you'll find the CODA Planner TARS model with 33.5 billion parameters in BF16, safe tensors weights, plus chat templates, and simple text-to-image-to-text usage snippets. Alright, the intro laid out the trade-off between planning and precise execution. Figure 1 shows the dual brain setup. The planner, called the Cerebrum, reasons from screenshots and history, while the executor, the Cerebellum, converts thoughts into exact mouse and keyboard actions. The top right panel highlights decoupled reinforcement learning, where rewards flow to the planner because the executor stays fixed. The rightmost strip illustrates improvement in planner thoughts after reinforcement learning, which leads to clearer, more goal-directed steps on the same Chimera X task. So, Figure 2 presents the overall training loop for the dual brain agent. The planner produces stepwise thoughts from screenshots and history, which the executor converts into precise mouse and keyboard actions, so action parameters like coordinates stay accurate. Rewards come from executed actions and flow back only to the planning tokens, which means the executor remains fixed while the planner learns. The feedback connection closes the loop and turns interaction outcomes into improved future plans. Alright, the last diagram outlined the planner learning loop. Figure 3 shows the exploration pipeline that supports training, with two parts that work together. Panel A illustrates specialist to generalist training. An initial agent learns with software-specific reinforcement learning to produce specialist trajectories, which are then stacked and distilled into a single generalist planner. Panel B depicts the distributed virtual machine system that feeds this process, where a controller dispatches tasks to many virtual machines and aggregates trajectories, so data collection scales efficiently. So the last diagram covered data collection at scale. Table 1 reports Science Board success rates, and it highlights that the two-stage agent leads across domains because the planner learns while the executor stays fixed. Average at 8 jumps to roughly 21% for the generalist, with specialists lower, and pass at 8 reaches about 40% plus. The gains appear across algebra, biochem, GIS, and astronomy, which signals robust generalization. Wrapping up, two takeaways stand out. Decoupled reinforcement learning lets a trainable planner improve while a fixed executor guarantees precise actions, and the two-stage specialist to generalist pipeline delivers strong cross-domain gains on Science Board. The broader implication is practical, reliable GUI automation for scientific software. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.